Welcome back. Now we're going to talk about electric forces and Coulomb's law. Electric force can be attractive or repulsive. We already discussed that the like charges repel each other, and if charges have opposite signs, they're going to attract each other. But how we can calculate this force between those two charges? Coulomb set up an experiment and determined experimentally Coulomb's law, the force, the magnitude of the electric force between two particles. And let's just look at this formula. We can see that it's proportional magnitude of those two charges. It's inversely proportional to the distance squared between those two charges. And there is also k in front of this ratio, just because we need some kind of constant. It's a proportionality coefficient. So Coulomb's law is given by this formula. Force is equal to k times q1 q2 over r squared. And what I didn't tell you yet, what is the constant k defined? What is the value for the constant k? And it has been determined that constant k is equal 9 10 to the 9. This is the easiest way to remember. Of course, if you want to use it, 8.99 10 to the 9, you can do that too, but in my calculations and in our class, we can always use just 9 10 to the 9. The direction of the force is always along the line that connects two charges. And repulsive force will give a positive value for force. This is between like charges, and attractive force then will give you a negative value for force. This will happen between unlike charges. This should basically just happen plus times plus, positive times positive gives you positive, negative times negative gives you negative, and positive times negatives gives you negative. So this comes from standard formula. But as always in physics, make a picture, charge, here's a force between two charges. If this is plus, this is negative, the forces are going to go this way. This is force that negative charge experience, this is force that positive charge experience. And otherwise you will have, if it's similar charges, plus, the force will go in the opposite direction. Something like that. Another way to describe Coulomb's law is use a different constant. This is what it is. Instead of k, this formula uses 4 pi times epsilon naught. Epsilon naught is another constant. It's called permittivity of free space. Just know that it exists. We're not going to use it. You don't need to remember. Just use always k. And relationship obviously is that between those two constants. So in this class we just use k. You go to 4 pi epsilon naught when you go to calculus-based physics, because it makes more sense to use it epsilon naught there. But for us, k is much easier and simpler. The form of Coulomb's law is very similar to Newton's law of universal gravitation. So if you remember Newton's law of universal gravitation, it was equal g times m1 m2 over r squared. Here's similarity. R squared in both cases. Property of first object, property of second object, and some kind of constant in front. So the one difference though, gravity is always attractive, but electric force may be as attractive. It also can be repulsive as well. So that's the difference. And of course the constant is different, and here's mass and instead of q, but the similarity is also in inversely proportional to r squared. Next one. Electric force is way stronger than gravitational force. The classical example that is on the slide is, let's compare electric force and gravitational force between electrons and protons. Those is just values from tables. Mass of electron, mass of proton, and gravitational constant. You can see it. And the same qualities are for electric force, charge of electron, charge of proton, and the constant. Let's just plug in those values. And what you'll see is gravitational force, mass of proton, mass of electron, distance between electrons. It's also known. I didn't show you it's in the picture, but it's a given value. So you can see it's very tiny. It's 10 to the negative 47. And electrical force is electrical force. You can plug in those values from here. You will get 8.74, 10 to the negative 8. Right away, you see the difference here. 47 or negative 8, big difference. So let's just do comparison over here. Divide y by another, and the difference is 210 to the 39th. This is a huge difference. So when proton and electron are next to each other, electric force is way stronger than gravitational force. You can just imagine how many zeros are here. 39 zeros. You'll get tired of writing all those zeros. There is another way to look at size of the electric force. Assume we have two boxes, each containing 1 gram of electrons, and it is 1 meter apart from each other. There's box 1, box 2, and there is 1 meter distance. And if we know mass of one electron, then we can calculate number of electrons in each box. It's 1.1 10 to 27. And then applying Coulomb's law, force equal K, Q1, Q2, basically it's the same, so we can write it as Q squared and divided by 1 meter squared. We can calculate that the force between boxes is 3 to 10 to the power of 26 newtons. This is really huge force. And it's almost a million times larger than the force between Sun and the Earth. So it's really huge force. You can imagine that. Maybe you can imagine that. But so why we don't really feel it on Earth all the time? It's simply because matter consists of approximately equal number of electrons and protons. So matter is electrically neutral, and the charge is equal 0. And so we don't really worry about the electrical force in our everyday time. As always in physics, we're going to be dealing with vectors. Force is a vector, and superposition of the forces is also valid. And if we are given two charges or more than two charges, we have to apply principle of superposition. And that means we just have to add all forces acting on a test charge or somewhere else to find sum of all forces, or net force. And that will give us understanding of what's physically happening with an object. Will this charge move, will stay put, how much force we need to apply to it in order to hold it in this position, and so on. So just look as given in this example. There is first charge, second charge double the size, and there is a test charge, and if this is, I guess, all positive charges, so charge Q1 acting on test charge Q2 with the force F1, and this charge 2Q acting on the same charge at 0 with this force F2. So you have to add those two forces using vector rules, head to tail, and the sum will be hence this one. This is the net force. Let's solve problem 16. That's the last part of this segment. There's two particles of charge Q and 5Q, and they're located at distance L from origin or alpha L from origin. And then we're placing a third charge right here. The third charge goes right here at the origin, and it's found that the force in it is 0, so it doesn't move anywhere. And the question is find alpha. So alpha question mark. Let's just look at the forces that act on this charge. Assume they all have the same charge positive. It doesn't really matter, you can repeat the same calculation if this charge is negative. So then, because this charge Q and unknown charge in the center have the same sign, the force acting on this charge is going to go this way, and it's going to be equal F1 capital Q, little q that we don't know, over L squared. Now if we look at this charge 5Q, the force acting on the test charge at the center is going to be directed in another to the left, so F2 is equal K 5 capital Q little q over L squared. No, alpha squared L squared. Yeah, now it's correct. What's important to know is that the sum of all forces is 0. That means F1 is equal F2 in magnitude, and we can solve it this way. Go to the next page so I have more place to write. Have K Q little q L squared is equal K 5 capital Q little q for the test charge in the center, alpha squared L squared. This is just this distance squared. What cancels out? Q cancels out, little q cancels out, L squared cancels out, K cancels out. What's left? Just write what's left. Have 1 equal 5 over alpha squared. Then alpha squared is equal 5, and alpha is equal radical of 5. So this is approximately 224, and this is your answer to the problem 16. That's the end of this segment.